laws, we have a bunch of them there that we talked about. We got Boyle, which is our P1 V1 equals P2 V2. That's obviously at constant temperature. One goes up, one goes down, basically. We have our Charles law. Our V1 over T1 equals V2 over T2. This is at constant pressure. Here, volume goes up, temperature goes up, volume goes down, temperature goes down. We also had our P1 T1 equals P2 T2. This is at constant volume. And this has a similar relationship. Pressure goes up, temperature goes up, and temperature goes down, pressure goes down. Obviously, as we talked about earlier, we need Kelvin on each of these situations here, right? We then saw, I think, Avogadro's law. That's at constant temperature and pressure. Putting all those together gave us the ideal gas law, which is PV equals nRT. Here, R being our gas constant of 0.08206. And obviously, the most restricted, as we talked about, we need atmospheres for pressure, we need liters for volume, obviously moles and Kelvin there. We also saw at the end the combined gas law, which is our P1 V1 T1 is equal to P2 V2 and T2 here, and obviously Kelvin as well for our temperature there. Any questions on any of those sort of gas laws that we talked about there? And again, as we talked about, really, if you get this one down, you pretty much can get all the top ones here pretty easily and solve for them. All right, so the next thing we're going to kind of talk about with gases is actually stoichiometry involving gases. And stoichiometry that involves gases really does work the exact same way as stoichiometry that doesn't involve gases. It's really in a basic gas stoichiometry problem, those 4 steps that we talked about, which is you want to make sure that you balance the equation. If it's not, you want to convert to moles. You want to do the actual stoichiometry part, which is the mole to mole relationship from the balanced equation. And lastly, you want to convert moles to some other unit. And just like regular stoichiometry problems, it is possible to have a limiting reagent problem as well that involves gases, and it works the same way. So again, if it happened to be a limiting reagent situation, obviously around there, you want to figure out which one's the limiting reagent before you sort of proceed. So really sort of the meat of the stoichiometry sandwich here is basically the same. It is just a little bit different on a lot of times these 2 steps, basically. And the difference oftentimes will come from how we get to moles, or at the end, how we get to like volume or something like that. And it will usually involve using the ideal gas law somewhere along the way. So somewhere along the way, it will usually involve using that ideal gas law. If you typically use it at the end, you most likely are going to be solving for volume. Not 100% of the time, but in most cases. If you use it up front, you most likely will be solving for moles if you kind of use it up front. And again, so these are very common places to use it. I would say probably this part is the most common. Like at the end, you use it and solve for the volume of gas you collected. So kind of like the experiment we did the other day where you collected all that hydrogen gas. One way you could solve is actually use the ideal gas law and do some stoichiometry. But that's the main difference between it, and everything else is basically the same. So why don't we look at one here together to sort of see how we go about this approach. So if we have this reaction here, P4 plus 4H2 makes a product. What is the volume hydrogen gas at 27 degrees Celsius and 1.25 atmospheres that is required to react with 5.65 grams of phosphorus? So if we do follow sort of our stoichiometry steps, the first thing we would want obviously is the balanced equation, which clearly here we have. We are given some information about sort of hydrogen gas, right? So that is obviously the gas here we're looking for. So if we think about the gas and some of the values that go with that, we have temperature, that's 27 degrees Celsius. We have a pressure that is 1.25 atmospheres. We are looking for a volume in this case. So this is a case where we're going to use really the ideal gas law at the end for hydrogen. We're going to use PV equals nRT. And if you just sort of check off sort of what is given to you and what you have, it will kind of help you with that. So we obviously have the pressure, we have the temperature. Again, we always have R, and we are clearly looking for the volume here. That means really the one thing that we are missing for hydrogen to do this is the moles of hydrogen. And that is really where the stoichiometry part of this problem is going to sort of come into play. We're going to use stoichiometry in this case basically to figure out how many moles of hydrogen we started with. And then once we have that, we could go into the ideal gas law at the end there and solve for volume. Any questions on sort of where we're going with this? Now, we clearly kind of use this information, which means that is really the only piece of information we kind of have left that is sort of not gas related, if you will. And we would then follow our second step in stoichiometry, which is take whatever they give us and convert to moles, right? And in this case, we do need to do that. So we would start with 5.65 grams of P4. We would go to the periodic table and look up phosphorus there, which is 3097. And we would use the molar mass for phosphorus to convert it into moles. So that is 4 times 3097 grams per mole. Again, that is the molar mass from the periodic table, is where that number comes from. That gets us something like, it's 123.9, by the way. So 5.65 divided by 4 times 3097 gets us 0.04561 moles of P4. So here, all I'm doing is converting the grams into moles because I ultimately need moles for my ideal gas law. Do I need the moles of P4 though? I don't need the moles of P4, right? Because we're looking for hydrogen gas. So this is again where the stoichiometry part comes into play. We're going to do our third step, which is go to the equation and find the relationship between P4 and H2, which looks like for every 1 mole of P4, I get 4 moles of H2. And that would be our next step here. We go 0.04561 moles of P4 using our stoichiometry here. 1 mole of P4 on the bottom, 4 moles of H2 up on top, and that will get us, we'll call it 0.182 moles of H2, which is the missing piece that I need up here for the ideal gas law. Now that I have used stoichiometry to get me to the moles of the H2, I do have everything I need now to basically use the ideal gas law, which is a very common in gas stoichiometry problems. That fourth step is you kind of use the ideal gas law here. So in that fourth step, we're going to use PV equals nRT. We're going to solve for volume. So the volume would be nRT divided by P. We do need to still check some units here and the pressures in atmosphere, so that's good. Obviously our moles are in moles, so that's good. But much like usual here, right, we do need to do that conversion for our temperature and take it to Kelvin. So we're going to do a 273 plus a 27. Going to give us 300 Kelvin on that conversion. So now that we have everybody in the right units, we just got to put it in there, and that would be 0.182 moles, 0.08206, which is our gas constant that we always have, and our temperature, which is 300 Kelvin, all going to be divided by the pressure, which was given to us at 1.25 atmospheres. Kelvins will cancel, moles will cancel, atmospheres will cancel. Is going to leave us liters as the unit that is left at this point. And let me write it up on top maybe so it'll be easier to see in this room. Yeah. So we have volume will be Rn, which was, we got there, 0.182. Worst room design for lecturing ever, this one. Can we put any more obstacles in the way of the actual board? That's right. We had 300 Kelvin up on top, and our pressure was 1.25, right? There you go. That might be easier to see, I hope. All right. So we're going to take 0.182 times 0.08206 times 300 divided by 1.25. And that's going to give us a 3.58 liters as our amount of hydrogen gas that would be produced in this particular case. Any questions on any of that there? Okay. So again, you could hopefully see what you can see in this room was the same 4 steps. We want to balance the equation, convert to moles, multiple relationships. So really the first 3 steps were pretty much identical to a normal stoichiometry problem. And again, a lot of times this is the main difference. Instead of maybe using molar mass at the back end there, you use the ideal gas law and figure out the volume. Any questions on any of that one there? Did I say one time the ATM? There was for the R. Yeah, it's over here on the bottom. Yeah, pressure. So no, those are all the units that go with R. So R has like 4 different units associated with it. And the units are basically liters times atmosphere up on top, divided by Kelvin times mole. All 4 of those units go with R. And they go with R so that when we put it in, like we just did here, pretty much everything will cancel except for 1. Yeah. Yep. Other questions? Okay. All right, so why don't you try one here, which is pretty much what you did in that experiment. You took some magnesium, you added some hydrochloric acid, there was bubbles, there was ooze, there was ahs. And you want to calculate the volume of hydrogen gas produced at STP if you started with 5 grams of magnesium and excess HCl. So give it a try. This is pretty much the identical calculation of what you need to do for that lab. Do for the theoretical yield for that experiment 17, based on the mass of your magnesium that you had. Obviously, you didn't have 5 grams. In this case, we are looking for the volume of hydrogen gas, which obviously is a gas. As at STP conditions, again, that means that the temperature is 273 Kelvin. The pressure is 1 atmosphere. Remember, we always have R. So, if we look at it again, the ideal gas law here, we have everything pretty much we need, except for the moles of the hydrogen gas. So very much like the previous problem here, we're going to kind of approach it using the only other number that's there, which is the 5 grams of magnesium. So we're going to do a stoichiometry problem to go from magnesium moles to hydrogen moles. Then we obviously can use the ideal gas law to do that. So first step there, we got our balanced equation. Second step is we're going to convert here to moles using the molar mass there from the periodic table, 2431 grams per mole. Going to get us call it 0.2057 moles of magnesium. Remember that we're not really interested in magnesium, but we need hydrogen. So that is, again, where the stoichiometry comes from. It is a 1-to-1 relationship between those two from the equation. That makes it pretty simple there. That's going to be 1 mole of magnesium on the bottom, 1 mole of H2 up on top, giving us 0.2057 moles of H2. Any questions up to there? At this point, we now have found, again, our missing sort of guy that we need. So this would be like step 3. We now could roll into step 4 here. Again, we're going to solve for volume, which would be nRT divided by P. Putting in our moles, which is 0.2057. Our R 0.08206, liters, atmosphere, Kelvin, and mole. Our 273 for our temperature, all divided by 1 atmosphere. For our pressure, again, atmospheres will cancel, moles will cancel, Kelvin will cancel, leaving us liters, and we end up with 4.61 liters of H2 would be produced. So again, this is pretty much identical to the calculation that you need to do for experiment 17, number 1 on the table for theoretical yield. Any questions on that? Yes. You absolutely could. That would be my next sentence, but yes, you could use that. We could solve this another way because we are at STP conditions. We actually don't need to use the ideal gas law. I got another page here, hopefully. Yeah, okay, yeah. Let's do it here so people can see it. So because we were at STP conditions here, we could use that 1 mole is equal to 22.414 liters at this point. And we could have just picked it up with the moles of hydrogen, which was 0.2057. So 0.2057 moles of hydrogen. And again, because it is at STP conditions, we could have avoided the ideal gas law and just rolled with this conversion. And we would get, obviously, this same answer, 4.61 liters. So you absolutely could have used it in this situation. It's a good reminder that if you didn't think about it or weren't sure if you could obviously still use the ideal gas law like we did there as well. Any questions on either way there? Again, a friendly reminder one more time that you should only use that at STP conditions. If it is not STP conditions, do not use it. Yes. Any questions on those stoichiometry problems? So really, again, sort of the same basic steps, just somewhere along the way, you're going to use that ideal gas law. Again, if you use it up front, probably going to solve for moles. If you use it on the back end, most likely, like we did here, going to solve for volume. Now, another sort of relationship in terms of stoichiometry does occur when we are at constant temperature and pressure. So as we talked about earlier, when we hit a constant temperature and pressure situation involving stoichiometry, we can revert back to our friend Avogadro, who, as we talked about earlier, I had many conversations with. And we can use Avogadro's law and sort of his relationship to sort of shortcut the stoichiometry calculation and make it a little bit easier without having to necessarily use the ideal gas law. Again, in this situation, you can still use the ideal gas law if you don't remember this sort of relationship or how to do it. So just to sort of show you it that way first, you can still approach it as a stoichiometry problem. Here, the temperature is 450 Kelvin and 5 atmospheres for the pressure. So if we wanted to know the volume of nitrogen gas, if we reacted with 9 liters of hydrogen gas, we actually can just approach it stoichiometry wise like a normal and use the ideal gas law. we are given 9 liters of hydrogen gas. So in this case, starting with the hydrogen gas, which is really what we're not interested in, after we have the balance equation, we can use PV is equal to nRT. And in this case, if we think about the hydrogen gas that's given to us, we have the pressure, we have the volume, we have R, and we have the temperature. That is what I was talking about earlier, that if you use the ideal gas law early on in the stoichiometry problem, you would be solving for moles in this case. So we would be using this to solve for moles, which would be PV over RT. And again, this is all for hydrogen, which is what we're sort of starting with in this reaction here. And the pressure is 5 atmospheres. The volume is 9 liters for the hydrogen. Our R, which is 0.08206. And our temperature, which is 450. And if we do all that, this will give us how many moles of hydrogen we have, which would be 5 times 9 divided by 0.08206 divided by 450 gives us about 1.219 moles of hydrogen. Remember, though, that we're not interested in hydrogen, but we're actually interested in nitrogen gas here. So this is where the stoichiometry would come into play between nitrogen and hydrogen. It is 1 mole nitrogen gives us 3 moles of hydrogen. So we would use that like a normal stoichiometry problem here. And again, 3 moles of hydrogen, 1 mole of nitrogen. That is going to convert us into moles of nitrogen, which is what we're interested in, which is 0.0406 moles of nitrogen. So this is really like the stoichiometry problem we were talking about, but here we're actually using the ideal gas law up front, step 1. Step 2 is, again, using the ideal gas law to get to moles instead of like grams a mole or mass. Step 3 here, doing our mole to mole sort of conversion from the equation. And now step 4, we're actually going to use the ideal gas law one more time here for nitrogen. And what we're going to try to solve for is the volume of nitrogen. So I'm just gonna go up high so hopefully people can see it. So we're going to use PV equals nRT for nitrogen. And in this case, we want to solve for volume, which would be V is equal to nRT over P. And at this point, the pressure and the temperature are still the same. So still the 450 Kelvin is still the 5 atmospheres. The R is obviously the same, and the N is what we just solved for there. So flipping it here, volume equals nRT over P. So our moles was 0.0406 for the nitrogen. Our R is obviously the same R. And in this case, our temperature is the same. Was it 450 temperature? I think. Yeah. And our pressure is 5 atmospheres. So this would be like the 4th step here, using the ideal gas law at the end to solve for volume, which is really common. So 0.0406 times 0.08206 times 450 divided by 5 gives us approximately 0.2998 liters, which is like 0.3 liters in this particular case. I didn't mess up any of the calculation there. One sec here. I want to make sure I punched everything in right here real quick. That's where I'm off. I have an extra 0. I'm sorry about that. is 0.406. There we go. So moving that there. Extra 0 not necessary here. 0.406. Gonna move me over to 3 liters. That's much better. There you go. Sorry about that. All right, so we get 3 liters here, which would again be our 4th step. If you kind of did a traditional sort of stoichiometry procedure, again, step 1, the balanced equation. Step 2, here we're using the ideal gas law to solve for moles. Step 3, the mole-to-mole relationship. And step number 4 here, using the ideal gas law on the back end of the calculation to solve for volume. First off, any questions on doing it this way? Don't screw up and write the wrong number. Good advice. All right, now there's a much simpler way of doing this problem because we're at constant pressure and temperature, and that is again using our relationship that we saw when we were talking about Avogadro's law. Because this is at constant pressure and temperature, we simply can do a liter to liter relationship instead of a mole to mole relationship. And that means that we could actually start with our 9 liters of hydrogen. And from the equation, from the coefficients, we see that for every 3 liters of hydrogen, we get 1 liter of N2. And that it would be exactly the same way as you would do a mole to mole relationship. And because it's at constant pressure, that's pretty much all you would need to do. You could take the 9 liters of H2 and use that liter to liter relationship and do 3 liters of H2 on the bottom, 1 liter of N2 on top. And lo and behold, we end up with 3 liters of N2, which is super easier than doing the ideal gas law at both ends of the steps. So this is sort of the benefit of Avogadro's relationship here. And again, you can only use this in a stoichiometry problem if the temperature and the pressure remain constant. So if those 2 guys remain constant for everybody, you could just bypass sort of all the big stoichiometry part there and jump to a volume to volume relationship. And it's a much quicker way of doing it. If not, you could still obviously use the ideal gas law and you end up with the same answer, provided you don't write down the wrong number. Yes. Any questions on that part of it there? All right, so why don't you try one here? What is the volume of sulfur dioxide gas will be reacted when 12 liters of oxygen is consumed at constant temperature and pressure via this reaction here? All right, so in this case, we're looking for the volume of sulfur dioxide, which is this guy, that will react when 12 liters of oxygen, which is this guy there, is consumed at constant temperature and pressure. So in this case, they actually didn't give you any numbers. So you obviously probably won't be able to kind of do the ideal gas law version. The good news is you could just really go right to the equation at this point, which is balanced. And just like we would do a mole to mole relationship, we could say from the coefficients that that is 2 liters of SO2 gives us 1 liter of O2. So identical to how we do mole to mole. In this case, because of the constant temperature and pressure, we could come up with that volume to volume relationship, which will allow us to pretty much directly calculate what we need. So we got 12 liters of oxygen, using that as really a conversion factor here. 1 liter of oxygen will give us 2 liters of SO2. Liters of O2 will cancel, gives us 24 liters of SO2 in this particular case. So these are really nice kind of quick stoichiometry problems that you can do when you're looking at sort of a volume to volume relationship that involves gases. As long as it's constant temperature and pressure, it's a good way to go. Any questions on stoichiometry involving gases? Okay. So next thing we're going to talk about is sort of what was going on when we did those experiments, which is partial pressures. Dalton law of partial pressures sounds very difficult, but it's really not a very difficult concept. The idea here is if we have a container that has like only 1 gas molecule in it, and that A is flying around, then the total pressure of that container is going to be pretty much a result of only the pressure exerted by gas A. Oftentimes, though, gases do come as mixture of gases. So maybe we got A gas molecules, B gas molecules, C gas molecules kind of flying around in the same container. All those different gas molecules are going to collide. There's going to be collisions, and they all basically are going to be contributing to the overall pressure of that mixture, where in this case, the total pressure would be the pressure of A plus the pressure of B plus the pressure of C in this case. Because they are each contributing to the overall pressure, they are what are referred to as partial pressures. That's basically what it means. They are partially contributing to the overall pressure of that mixture. The total pressure in a laboratory situation is what you did here, the barometer reading. Yes, is basically where you get your total pressure from. How do we get the partial pressure of each of these gases? Well, the most common way to get the partial pressure is the ideal gas law. And PV equals nRT gives you nRT divided by V. You would essentially just do the ideal gas law in the case on the right 3 different times. One for A, one for B, and one for C. And once you figured out each of those individual pressures, those would be the partial pressures of each of those gases, you simply just add them together, and that will give you your total pressure for that mixture of gases. The good news is that it is a mixture of gas, which means all 3 of these guys are flying around in the same container, which means the volume in every single calculation is identically the same. Also means that that container is sitting in the same room, which means the temperature for all these gas calculations will be the same. And obviously R, which is a constant, will be the same. So really the only difference that you typically will need to do in a partial pressure calculation is to figure out the moles of each of the gases and put the correct moles in. All the other values will still be the same for everybody because they're all in the same container. You just got to also obviously make sure everybody's in the correct units for the ideal gas law. Any questions on that there? That's pretty much what this says. So again, we could do this, and you might be wondering, well, isn't there multiple gases? Aren't they sort of interfering with each other and stuff like that? So earlier we talked about the idea of ideal gases. And one of the things that makes something an ideal gas is the idea that even if you have different gases near each other in the same container, in an ideal situation, they will pretty much ignore each other. They won't interact with each other. They won't basically interact, repel, collide with each other. It is almost like you could imagine each of those gases being in the container by themselves. And that's sort of what an ideal situation is. That's really one of the things that makes something an ideal gas, is the idea that there is no interaction between other gases. There's no repulsive forces. There's no attractive forces. So that's why we could actually do these type of problems like this, where everybody is in the same container, and we can basically just do it separately. So why don't we try one here? 5 grams of helium plus 5 grams of neon in the same container. What is the partial pressure of each gas and the total pressure here? Helium is 4.003 and neon is 2018, it looks like. In the same container flying around, which means the volume for each of these guys will be 2.5 liters, and the temperature for each guy will be 27 degrees Celsius, which we automatically know we should convert to Kelvin, which would be 300 Kelvin. Now we have 5 grams of each of those things. Just going to get rid of some of that so it can write a little bit higher up there on the screen. So basically, if we think about the ideal gas law, as we talked about, we can use it for each of the gases individually here, even though they're in the same container. So obviously we have the temperature, we always have R, we are looking for the pressure, and we have the volume given to us. So we do need to figure out the moles of each of those gases to begin with. So we had 5 grams of helium, and that is 4.003 grams per mole from the periodic table. That gets us 4.003, 1.25 moles of helium. We also want to convert our grams of neon into moles as well because we need it. That's 2018 grams per mole. So 5 divided by 2018 gives us 0.248 moles of neon. Any questions so far on that? That is really the missing piece that we need for each of the gases. So like I said before, even though they're flying around together, the ideal gas part of it means you can think of them as being there by themselves. They really won't behave or interact with each other. So we're going to first solve for the pressure here of the helium, which would be nRT divided by V, and putting in our numbers for helium, which is 1.25 moles, our R, which is our constant, our temperature converted to Kelvin, which is 300, all divided by our volume, which was 2.5 liters. Everything's going to cancel out except for atmospheres here. So that will give us 1.25 times 0.08206 times a 300 divided by 2.5. And that's going to give us approximately a 12.3 atmospheres. The 12.3 atmospheres represents the partial pressure of helium in this particular case. Any questions on that calculation there? We're going to do the exact same calculation for neon. The only difference is we're going to use the moles for neon. And that would give us the partial pressure of neon would be our 0.248 moles, which again is our moles for neon. Every other value is going to be exactly the same since they're in the same container. And if we do that there, we end up with a 0.248 times 0.08206 times a 300 divided by a 2.5 gives us a 2.44 atmospheres. That would be the partial pressure of neon in this particular case. Any question on either of those two calculations? How would I find the total pressure? Yeah, the total pressure is just found by simply adding those two together. So the total pressure would be 12.3 plus 2.44. And that gets us 14.7 atmospheres. So this is a very common sort of partial pressure type problem. It really is just an ideal gas law where you solve for really each of the gases individually. And when you do that, because they're in a mixture, they're considered partial pressures rather than just pressures. And the total pressure found by adding it. The major contributor to the pressure in this mixture is which gas? It is the helium at 12.3 atmospheres, right? The reason for that is, anybody have a guess? The reason for that is in the molar mass, helium is 4 grams, neon is 20 grams, helium is much, much lighter, which means it is flying around a lot faster and causing more collisions. It has a higher velocity, which when you go to 1A, you'll calculate the velocity of things like this, but it has a much higher velocity and moving around a lot faster, causing more collisions than the slower moving neon. Any questions on this type of partial pressure problem here? All right, hang in there, almost there. The second type of partial pressure situation happens just like it did in the experiments that we did. And that is, as we talked about, when we do create our sort of collect gases where water's involved, as we talked about, we, in addition to the gas that we collect, we get basically water vapor that occurs. And that's just a reaction of are a combination of basically collecting your gas like we did in water. So as the reaction is happening, obviously it's going to heat up some of that water. So we get the gas we're interested in, but we also get water vapor that happens as well. And this is really two gases that end up in the same location. This is really a partial pressure situation that occurs. So as we talked about when we did those experiments, and as you want to make sure that you do when you do the calculations, we do have to basically correct for the vapor pressure of water, because although we did collect the water, we're really not interested in it. In the example of the magnesium and the hydrochloric acid, we were interested in just the hydrogen gas that we collected. In the case of the second one we collected oxygen gas. And in both of those cases, because we basically collected the gas with the water, we got basically some water that came along basically for the ride. And there's your sort of the one. So an easy way to sort of correct this is the total pressure is equal to the pressure of the gas you're interested in plus the vapor pressure of water, which is what this is, the vapor pressure of water. This, as you know, and as you hopefully got off of this list, if you didn't, you might want to take a picture of it. By the way, you might want to take a picture of it since you might need it for a post-lab question, I think, on one of those, the vapor pressure chart, just in case. You could look up that value in an actual table. So what we typically end up doing is, this is a very easy partial pressure situation. This is a subtraction that basically occurs. The pressure of the gas is equal to the total pressure minus the vapor pressure of water. The total pressure in your situation, as I mentioned before, is the barometer reading or the atmospheric pressure. That is basically your total pressure, and obviously the vapor pressure of water you find from the table. That is the exact experiment that you did, I think, pretty much. And you created obviously the oxygen gas here, went through the tube, came up through here, got the oxygen gas, but again, the result of that was you got the water. So it's really important when you use the pressure in those calculations that it is just the pressure of the gas. You got to do that correction to take off the vapor pressure of water so that you have the right pressure. So in a problem like this, a sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of the oxygen gas? So this is basically a very similar situation to what occurred in that second experiment as well. In a book problem, how do you know it's sort of this situation? There's a couple of keywords, and these are the keywords. It's saturated with water vapor, or it says something like you collected it over water or something like that. So something that involves water is usually the key that you have to use that relationship that we just saw, which is the total pressure is equal to the pressure of the gas plus the vapor pressure of water. In this particular case, the total pressure is 753 torr. The pressure of the gas that we're interested in, and they were nice enough to give you the value here in the problem. A lot of times they are not nice like that, and there is a table in the chapter usually that you might have to look it up. Again, very much like the table that's hanging up there on the wall, and it's based off of temperature, just like you did over there. And in this case, it would be 31.824 torr. Rearranging gives us the pressure of the gas is equal to 753 torr minus the vapor pressure of water. And if we did that, we would end up with 753 minus 31.824 gets us approximately 721 torr. They do want it in atmospheres, so to convert torr into atmospheres, we divide by 760. And that gives us 760, 0.949 atmospheres. This would be the pressure of the gas that has taken the water vapor out of it. It is sometimes referred to as the pressure of the dry gas, because you have taken away the pressure because of the water. This is definitely the pressure that you would want to use in any calculation. So in both of those experiments, in 17 and 18, for the hydrogen gas, you want to make sure that you do this correction. And then for all the pressure for the hydrogen gases you need to use in a gas law, you need to make sure you use the one that you've subtracted off the water vapor pressure. Same thing with the other one, which is the oxygen gas. You got to make sure you subtract it off. And then for all the rest of the calculations that involve the pressure of the oxygen, you need to make sure that you are using just that one and not the one that has not the total pressure from the barometer. Any questions on that there? Okay. So the last thing we're going to talk about here is this little chart here, which is the kinetic Mucker theory of gases. We've kind of talked about a number of these things, but these are really the main parts of it. Gases are obviously very tiny particles, or your atoms or molecules. The particles are really small compared to the distances between them. So number 2 here is one of the things that makes something an ideal gas law, or an ideal gas, is the idea that we assume that the actual volume of the gas itself is 0 compared to the container. The container's volume is much larger than the actual gas. So that is something that is sort of an ideal situation. If you think about a lot of problems that you read, they talk more about the volume of the container that things are in rather than this is the volume of the gas. And that's the reason why in an ideal situation. Particles are in constant motion. They're colliding with the walls of the container. Obviously, these collisions, as we talked about, is what causes the pressure. The more collisions, obviously, the higher the pressure. The less collisions, the lower the pressure. And number 4 here is the second thing that makes it an ideal gas, is basically why we could do our partial pressure calculation. They're assumed to have no attractive or repulsive forces between different gases. So again, even though there's maybe a mixture of different gases in there, in an ideal situation, which is pretty much every situation, unless you get to really extreme pressures or low temperatures, they really will not interact with one another. It's only at those high pressures and low temperatures you get real gases, as we talked about earlier today, that they do interact, but we definitely don't come across any of those in here. The average kinetic energy of the gas molecules is related to the temperature. So as we talked about, if you increase the temperature, the gas should be flying around a lot faster. If you lower the temperature, it should be obviously moving a lot slower. Any questions on our big gas